All right, Stella, sorry we got knocked off the year. It happens. It's not your fault. Um, I'm going to finish this problem here, the sine of x. In order to find the power series for the sine of x, we're going to have to integrate the Taylor power series for the cosine of x. So integrating x squared with respect to x, we would be left with x cubed using the power rule of integration divided by 3. Plus, we got 1 over 4 factorial. The antiderivative of x to the 4th power with respect to x is x to the 5th power over 5. Over 5, just over 5, not 5 factorial, excuse me. It's just over 5. All right, minus 1 over 6 factorial times the antiderivative of x to the 6th with respect to x is going to be x to the 7th power over 7, and back to a plus here. Okay. Well, actually back to a plus 1 over 8 factorial times the antiderivative of x to the 8th power with respect to x is going to be x to the 9th power over 9. All right. So what we have here is we have x minus, now do you agree that 3 times 2 factorial is really 3 factorial? 3 times 2 factorial is really 3 times 2 times 1, which is what, 3 factorial? Likewise, 5 times 4 factorial is really 5 times 4 times 3 times 2 times 1, which is really what, 5 factorial? Okay, so therefore we can combine this and call this 3 factorial. So we're going to have minus x cubed over 3 factorial. Plus, this is going to be x to the 5th power over 5 factorial. Minus 6 factorial times 7 is really 7 factorial. So we have x to the 7th over 7 factorial. Plus, this is going to be x to the 9th over 9 factorial. 9 times 8 factorial is 9 factorial. Minus, et cetera, et cetera. So on and on this goes. So therefore, if this is our first term here, all right, this is, well, our first term, this is our second term, third term, fourth term, fifth term. Let's try to write the power series for sine of x. What's the relationship between 0 and the exponent on x? 0 and 1, 1 and 3, 2 and 5, 3 and 7, 5 and 9. Do you agree that our exponent is always odd for all these powers of x? Always odd. So therefore, we can start to put together our power series notation for the sine of x. K goes from 0 to infinity. Notice we also have an alternating series where our first term is positive, second term is negative. So we must have, or insist that we have negative 1 to the k power. When you put 0 in for k, negative 1 to the 0th power is a positive 1. When k is positive 1, you put positive 1, negative 1 to the first power is negative 1, et cetera, et cetera. So this will account for the alternation in sign. Now, as far as the powers of x are concerned, x is always raised to an odd power. So how do you go from 0 to 1, 1 to 3, 2 to 5, 3 to 7, 5 to 9? This is 4 to 9, excuse me. This is your a sub 4 term. 4 to 9? Well, you would have to have 2k plus 1. Because when k is 0, you put 0 in here, you'll have 2 times 0 plus 1, which is 0 plus 1 or x to the first power. Then you put 1 in for k. 2 times k is 2 times 1 rather is 2, and 2 plus 1 is 3, third power. Put 2 in for k. 2 times 2 is 4. 4 plus 1 is 5, fifth power. That'll count for the proper power on x. Now this is going to be divided by, notice our factorial here. Technically, This is going to be 1 factorial here. So how do you go from 0 to 1, 1 to 3, 2 to 5, 3 to 7, 4 to 9? Well, it's going to have to be 2k plus 1 factorial down here also. Okay, and you have the power series for the sine of x. So that would be the Maclaurin power series for the sine of x. All right, so hopefully that helps out with that problem there. So we started with the cosine power series, and by integrating each of the terms, we were able to derive ultimately the power series for the sine function there. Okay. All right, let's look at the next problem that was on the docket for today. Let's see here. Next problem is they want you to find the Maclaurin. Well, we already did that. Next one is they want you to find the Maclaurin series for 1 over 1 minus x and its interval of convergence. Okay, 1 over 1 minus x. All right, now to do this problem here, and this is page number 4. Okay, to do this problem here, 1 over 1 minus x. Notice 1 over 1 minus x looks hauntingly familiar to the sum of an infinite geometric series. Recall, I want you to recall that if we have an infinite geometric series, okay, an infinite geometric series, do you agree that the sum of this infinite geometric series is going to be the first, it's going to be the first term divided by 1 minus the common ratio? Remember we worked with that in the past, the sum of an infinite geometric series. Doesn't this look hauntingly familiar to this? So here's what we're going to do here. I'm going to use this to rewrite the power series for this using my infinite geometric series here. So take a look at this. Do you agree that 1 over 1 minus x is really equal to a sub 1 over 1 minus r, where our first term of our geometric series is going to be equal to 1, and r is going to be equal to what? Just x. Do you agree? R is just equal to x. So now we're in business, because we know, all right, we know that our first term in our geometric series has to be what? 1. Okay. And our common ratio has to be what? Has to be x. So therefore, I can write the power series for 1 over 1 minus x using this infinite geometric series here. So this is going to be equal to let's see, that's going to be equal to k equals 0 to this is actually our first term here, would be 0, a sub 0, 0 to infinity. Our first term of which has to be, this would be a sub 0, your first term has to be 1, would be 1 times your common rate. 1 is your first term when k is 0, and your common ratio would have to be what? X, right? X. So we put x in for r here, the common ratio. So we have x to the k power. And there you go. This would be the power series expansion for 1 over 1 minus x. That would be it. All right. Or we could just say that this is the infinite geometric series of x to the k power. So this would be the power series right here for 1 over 1 minus x. And now they want you to find the interval of convergence here. Interval of convergence. So to do that, we look at the ratio test for our power series here. So we have the limit as k approaches infinity of the absolute value of our k plus 1th term over our kth term is equal to the limit as k approaches infinity. Our k plus 1 term is going to be x to the k plus 1 divided by x to the k. So this is going to be equal to limit as k approaches infinity. Now we have one more factor of k in the numerator than we do in the denominator. So we're just going to be left with, when we divide these like bases, we subtract k from k plus 1, we're going to be left with just x. And we must insist that this be less than what, 1? Do you agree? This must be less than 1 for our power series to be convergent. Now notice the limit as k approaches infinity no longer has any relevance here because we don't have k appearing anywhere in here. So therefore, we can conclude then that the interval of convergence is the absolute value of x being less than 1, which implies that x would be less than between 1 and -1. This would be your interval of convergence. You might want to test the endpoints to see if your series is convergent at the endpoint. So like if I let x be equal to the left endpoint of this interval -1, and I replace x up here with -1, then my power series would become -1 to the k power, which is an alternating series. Okay. 1 times -1 to the k power. This could not be shown to be convergent by the alternating series test because the limit as k approaches infinity of 1 is equal to 1, which is not equal to 0. So the alternating series test fails. But we could use the nth term divergence test to show that the series diverges at x equals -1. Subjecting this to the nth term test, the limit as k approaches, this is k, approaches infinity of 1, of just 1 is equal to 1, which is not equal to 0. So this series diverges at x equals -1. Now when x is equal to +1, testing the right endpoint of this interval of convergence, we replace x with 1. And when we do so, we get this series here. K goes from 0 to infinity of 1 to the k power. But this is just going to be what? 1 plus 1 plus 1 plus 1, which obviously does not converge, but it diverges. And the nth term test can easily show that. The limit as k approaches infinity of 1 is equal to 1, not equal to 0. So our series diverges at x equals 1. Hence, our interval of convergence is strictly going to be this for the power series expansion of 1 over 1 minus x. So this is your interval of convergence for 1 over 1 minus x. Okay. Hopefully that one made sense there. Let's see what else we got here. Now this problem says, we showed that the nth order Taylor polynomial for e of x centered at 0 is this. We can extend this to say that the Maclaurin series of e to the x therefore is the same thing. Okay. With interval of convergence of all real numbers. I think I showed you this in the past. This is the power series expansion of e to the x power. Find the Maclaurin series for e to the negative 2x power and its interval of convergence. All right, so this is an interesting problem here. Let's see, this is page number 5. All right, so let's look at this one here. So therefore, we know that e to the x is equal to the Maclaurin series, k goes from 0 to infinity, of x to the k power over k factorial. So we know this right here, okay? Now, they want us to find the power series for e to the negative 2x power. Well, here's what we can do. You agree I can literally replace x here with negative 2x. And so therefore, wherever I see x in my power series, I can replace x with negative 2x. So therefore, the power series expansion of e to the negative 2x power is going to be x replaced with what? Negative 2x. And that'll be to the kth power. And that sits over k factorial. There you go. You now have the power series for e to the negative 2x power. That's what it would be. And they want us now to find the interval of convergence here for this power series. And to do that, we use the ratio test. So here we go. Limit k approaches infinity of the k plus 1th term divided by the kth term. And this is the limit as k approaches infinity. The k plus 1 term is going to be negative 2x to the k plus 1 power divided by k plus 1 factorial. And this is all going to be divided by negative 2x to the k power divided by k factorial, which is the limit as k approaches infinity. This k factorial comes up and joins this, and this will drop down and join this. So we're going to have k factorial times negative 2x to the k plus 1, and that sits over k plus 1 factorial times the negative 2x to the k power. So this is equal to the limit as k approaches infinity. Now, k factorial divided by k plus 1 factorial is going to be 1 over k plus 1. We've already shown that many times. And dividing negative 2x to the k plus 1 power by negative 2x to the k power, we have one more factor of negative 2x in the numerator. So we're just going to have negative 2x. Hence, now as we allow k to approach infinity, notice this fraction is going to approach 0. So this entire fraction is going to approach 0. And so therefore the limit of this is equal to 0. But the radius of convergence, remember, is 1 over the limit. So the radius of convergence is going to be infinity. And so there you have it. The interval of convergence, therefore, the interval of convergence for e to the negative 2x power, whose power series expansion is negative 2x to the k power divided by k factorial. K goes from 0 to infinity, is going to be all real numbers, negative to positive infinity. And we're done with that problem there. Okay. So that would be the interval of convergence for a new function called e to the negative 2x power, which, in all honesty, kind of makes sense. Because if you graph e to the negative 2x power, you're going to see that the graph is going to look like this. And you can see that this graph is, continuous for all real numbers. And so it kind of makes sense that the interval of convergence for the power series for e to the negative 2x would converge for all real numbers also. Okay. All right. Hopefully that one helps out with that problem there. Now here they want us to expand x plus y to the sixth power. And this is actually getting into what's called the binomial theorem in college algebra. Call this page 7 here. So they want you to expand x plus y to the sixth power here. And to expand this, what we can do is, I don't know if you've ever heard of this before, but it's called Pascal's triangle. Pascal's triangle provides us with coefficients of raising a binomial to a power. This is Pascal's triangle. I just want to show you here. One out here. All right, this is called Pascal's triangle. It's an amazing triangle here in the way it's constructed. It's very symmetric. How we get 2 here is we add 1 and 1 together to get 2. How we get 3 here is we add 1 and 2 together to get 3. 2 plus 1 here gives you 3. 4 is obtained by adding 1 and 3 together. 6 is obtained by adding 3 and 3 together. 4 is obtained by adding 3 and 1 together. And on this goes. 5 is obtained by adding 1 and 4 together. 10 is obtained by adding 4 and 6 together. 6 plus 4 is 10. 4 plus 1 is 5, etc. 1 plus 5 is 6. 5 plus 10 is 15. 10 plus 10 is 20. 10 plus 5 is 15. 5 plus 1 is 6, etc. All right, this is called Pascal's triangle. And what do we use this for? Well, what it's used for is to raise binomials to powers. For instance, this row would be raising a binomial to the second power. Okay. If you take a plus b and expand it out, you can see that you would get a squared plus 2ab plus b squared. Now, I want you to draw your attention here. You see this 1 here? This 1 is the leading coefficient here. This 2 is the coefficient in front of the middle term. This 1 here is the coefficient in front of the b squared. So if I was to take, okay, and another key observation here is this. Notice that the first term starts out at the power that the binomial is raised to. So a to the second power, and the second term starts out at the 0th power. Technically, this is a squared. Technically, this is a squared times b to the 0th power. Then what happens is for subsequent terms, the degree of a decreases by 1 and the degree of b increases by 1. So a to the second power decreases down to a to the first power. B to the 0th power increases by 1 to b to the first power. Now a's power decreases down to a to the 0th power, and b's power increases to b to the second power. And so you can see that we do get back a squared, this is 1, a squared plus 2ab plus b squared. All right. So like if I was to take right here, if I was to take our polynomial, which is x plus y, and raise it to the 6th power, this row is going to give us, okay, the coefficients of that expansion. This row gives you the coefficients of a binomial raised to the 3rd power. This road gives you the coefficients of a binomial raised to the fourth power. This row gives you the coefficients of a binomial raised to the fifth power. This row gives us the coefficients of a binomial raised to the sixth power. Specifically, it's our binomial x plus y raised to the sixth power. All right, so let's take x plus y and raise it to the sixth power by using this Pascal's triangle here. So therefore, x plus y rather to the sixth power is going to start out with a coefficient of 1. Okay, so we start out with a coefficient of 1 here. 1, and x starts out being raised to the power that the binomial is being raised to. So 1x to the sixth times y to the 0th power. This is technically y to the 0th. Plus, now our next coefficient is 6 by Pascal's triangle. 6, x's degree decreases by 1 down to x to the 5th, and y's power increases by 1 to y to the 1st. Plus, this coefficient, next coefficient is 15. Plus 15 times x's power decreases by 1 down to x to the 4th. Y's power increases by 1 up to y squared. Plus 20, the next coefficient is 20. X's power decreases by 1 down to x cubed. Y's power increases by 1 to y cubed. Plus, the next coefficient is 15. X's power is down to x squared. Y's power is up to y to the 4th. Plus, the next coefficient is 6 over here. X's power decreases by 1 down to x to the 1st. Y's power increases to y to the 5th. Plus, finally, 1 is the last coefficient. X's power is now down to the 0th power. X to the 0th power is 1. Y's power increases to 6. Y to the 6th. I want to draw your attention here. Notice when you add these exponents together, for any term, you always get 6, which is equal to the power that the binomial is raised to. 6 plus 0 is 6, 5 plus 1 is 6, 4 plus 2 is 6, 3 plus 3 is 6, 2 plus 4 is 6, 1 plus 5 is 6, and 6. This would be the expansion of x plus y to the 6th power. And y to the 0th power is just 1. So therefore, we have x to the 6th plus 6x to the 5th y plus 15x to the 4th y squared plus 20x cubed y cubed plus 15x squared y to the 4th plus 6xy to the 5th plus y to the 6th. Whoops, y to the 6th power. All right, so there you go. That would be the expansion of x plus y to the 6th power, making use of Pascal's triangle. If we wanted x plus y to the 5th power, we would use this row to generate our coefficients of each term. If we wanted to raise x plus y to the 4th power, we would use this row to generate the coefficients of each term. Actually, these coefficients or these numbers come from the combination function we talked about. Like this 2 comes from, let's see, 0, 1, 2. So this would be 2 in combination with 1. This would be 3 in combination with 1, 3 in combination with 2. This would be 4 in combination with 1, 4 in combination with 2, 4 in combination with 3. This would be 5 in combination with 1, 5 in combination with 2, 5 in combination with 3, 5 in combination with 4. Finally, this would be 6 in combination with 0. So this 6 here comes from 6 in combination with 0. This 15 comes from 6 in this is 6 in combination with 1, excuse me. This 15 comes from 6 in combination with 2. 20 comes from 6 in combination with 3. 15 comes from 6 in combination with 4. 6 comes from 6 in combination with 5. Okay. That's how we're generating these numbers for Pascal's triangles. They really are combinations. All right, so that gives you an idea as to where they're coming from there. But Stella, that would be it. That would be the expansion of x plus y to the 6th power. It would be this long old polynomial down here. And you got to admit, using Pascal's triangle is a lot easier in expanding this than multiplying this by itself 6 times, which would be extremely cumbersome. Okay. All right, so that problem is done. Now here they want you to calculate the 1/2 in combination with 3. All right, so 1/2 in combination with 3. To do that, we will have to go all the way back at the top and look at that general combination for all real numbers. So I'm sorry, hold on a second here. We got to go back up here and look at this. So we're going to have to apply in general P in combination with K, which according to this formula is P times P minus 1 times P minus 2 times ... times P minus K plus 1 all over K factorial. Okay. All right, so let's try to use this formula here to see how we would generate 1/2 in combination with 3 here. Tell you what, just to see how this formula works here, let's just try a simple problem that we know the answer to. For instance, if I wanted to evaluate, let's say I want to evaluate 3 in combination with 2, which would be written this way here, correct? 3 in combination with 2. Well, how would we do that? We would go 3 factorial divided by 3 minus 2 factorial at times 2 what factorial. Agree? Based on the formula that I showed you earlier. Okay, based on that formula I showed you earlier. So what would this evaluate to? Well, 3 factorial is, for now, 3 factorial. This is 3 minus 2 or 1 factorial times 2 factorial. 3 factorial is 3 times 2 times 1, and 1 factorial is 1, and 2 factorial is 2 times 1. So this all cancels, and it leaves you with just 3. Okay, just 3. Now let's try to use this formula to reconcile 3 in combination with 2 here, using this formula. 3 in combination with 2. So my P is really a 3. My P is a 3. My K is a 2. So this is really going to be 3, following this formula, 3 times 3 minus 1 times 3 minus 2, okay, times, this goes from 3 minus 2, which is 1, plus 1 is 2. So we would have to go 3 times 3 minus 1 times 3 minus 2 times ... all the way down to 3 minus K. K is 2 here, plus 1. And this would all be divided by 2, which is K, 2 factorial. So what does this give us here? This is going to be, now what does this give us way over here to the right? This is 3 minus 2, which is 1, and 1 plus 1 is 2. So we are only going to go down to 2 here. We only are to go down to 2. 3 minus 2 is 1, 1 plus 1 is 2. So we start at 3 times, and then we go down to just 2. 3 minus 1 is 2, and that's where we stop. This tells us where to stop. So this tells us where to stop, okay? So we go 3 times 3 down to 3 minus 2 is 1, 1 plus 2, 1 plus 1 is 2. So we go from 3 down to 2. So we only go down from 3 down to 3 minus 1, or 3 times 2, over 2 factorial. But do you agree this is 3 times 2? 2 factorial being 2, the 2's cancel, we're left with 3. Do you agree we get the same answer if we were to use this formula here to compute this? So now here's what we're going to do. We're going to apply this formula here to our combination, which is 1/2 in combination with 3. All right, so therefore we have to take 1/2 in combination with 3, where our 1/2 is P. Our 1/2 is P, and our K is 3. So let's look at the last number that would be in this expansion in the numerator. The last number in our numerator is going to be 1/2, which is P, minus K, which is 3, plus 1. This is to say the last number in our expansion is going to be 1/2 minus what? Well, 1/2 minus 3 is 1/2 minus 3 over 1 plus 1. Getting a common denominator of 1 and 2, which is 2, this would be 1/2 minus 6/2. This is really 6/2 plus 1. Because another name for 3 is 6/2, correct? So 1/2 minus 3 is 1/2 minus 6/2 plus 1. So 1/2 minus 6/2 is negative 5/2 plus 1. But another name for 1 is 2 over 2, isn't it? So this would take us down to negative what? Negative 5/2 plus 2 is negative 3/2. So therefore, we're going to start with P. Our P is 1/2. We're going to start with 1/2, but then we will terminate the expansion in the numerator when we get down to negative 3/2. Negative 3/2 is the stopping point. That would be your P minus K plus 1. So here we go. We start with P being 1/2. Put 1/2 in here. So we got 1/2 times 1/2 minus 1. And you agree 1/2 minus 1 is negative 1/2. So we don't stop here because negative 1/2 is not our stopping point of negative 3/2. We got to go one factor more. Well, 1/2 minus 2. 1/2 minus 2, do you agree, would be my stopping point of negative 3/2 here. So my numerator expansion just goes out to this. Because again, keep in mind, this tells you where to stop. And I evaluated P minus K plus 1 when my P is 1/2 and my K is 3. And I found my stopping point had to be negative 3/2. So we start with the numerator expansion by letting P be 1/2. Then 1/2 P minus 1 is 1/2 minus 1, which is negative 1/2, times P minus 2. 1/2 minus 2, that gives me my stopping point of negative 3/2. Well, this is going to be over our denominator, which is K factorial, which would be 3 factorial, K being 3 here. And Stella, all we have to do now is just evaluate this, and we'll have our combination of 1/2 down to 3. So this is going to be 1/2. What's 1/2 minus 1? That's negative 1/2. 1/2 minus 2 is really 1/2 minus 4/2. 1/2 minus 2 is 1/2 minus 4/2, which is negative 3/2. Negative 3/2. And this sits over 3 factorial. But what's 3 factorial? That's 3 times 2 times 1, which would be 6. All we have to do is clean this up, and we have our answer for 1/2 in combination with 3. All right, so what does this clean up to give us here? Hold on a second. Let me see what page this is. This is 8. All right, so this will be page 9. So therefore, we just clean this up here. What's 1/2 times negative 1/2? That's negative 1/4. And negative 1/4 multiplied by negative 3/2 would be positive. This is negative 1/4 times a negative 3/2 is 3 what? 3/8. 1/2 times negative 1/2 is negative 1/4 times negative 3/2. That's over 6. This is going to be positive 3/8 divided by 6. This 8 comes down and joins a 6. So this is going to be 3 over what? What's 6 times 8? 48. So this is going to be 3 over 48. But we can reduce 3 over 48 down to 1/16. And therefore, it looks like, Stella, we have answered our question. 1/2 in combination with 3 is going to be 1/16. And there's your answer for that problem there. Okay. All right. So that's how we do that problem there. Well, that one's done. Now here it says for this problem, let P be a real number. Find the first 4 derivatives of 1 plus x to the pth with respect to x and evaluate each derivative at 0. Then choose the formula for, in general, the kth derivative of 0. All right, so we'll try that. So here we go. We're going to try to generate some derivatives of f of x being equal to 1 plus x to the p power, where p is just some sort of a real number. They want us to find the first 4 derivatives of this and evaluate the derivatives at 0. So the first derivative of this would have us using the chain rule. We have a blob raised to the p power. We bring the p down in front times the blob raised to the power decreased by 1. Times technically the derivative of the blob, but the derivative of 1 plus x is just 1. This would be the first derivative. And if we were to evaluate this first derivative at 0, which they want us to do, we put 0 in for x, we would have 1 raised to the p minus 1 power. 1 plus 0 is 1, 1 raised to the p minus 1 power. But do you agree that that would just be what? 1 raised to the p minus 1 power would be what? 1? Isn't that true? So like when we raise 1 to any power, we always get what? 1, don't we? Okay. Now the second derivative of x with respect to x, we use the power rule again. We have p times this blob raised to the p minus 1 power. We bring the exponent down in front, multiply it by what's out there, namely the p, and then we raise the blob to the exponent decreased by 1. So p minus 1 is p to p minus 2. Technically times the derivative of 1 plus x, which is times 1 again. So this is our second derivative. Now to evaluate our second derivative at 0, we replace x with 0. And when we replace x with 0, this is just going to be 1 to the p minus 2 power. So we're going to have p times p minus 1 times technically 1 to the p minus 2 power, which is just 1 again. So our second derivative is just p times p minus 1. That's your second derivative, evaluated at 0. The third derivative of this function is going to have us bringing the p minus 2 down in front and multiplying by all this that exists. So we have p times p minus 1 times p minus 2 times 1 plus x raised to this power decreased by 1. P minus 2 minus 1 is p minus 3 power. Times technically the derivative of 1 plus x, which is times 1 again. Evaluating our third derivative at 0, replacing x with 0, 1 plus 0 is 1, but 1 to any power is just 1. So this is just going to be 1. And so therefore we're going to be left with our third derivative evaluated at 0 is just going to be p times p minus 1 times p minus 2. That's your third derivative evaluated at 0. Finally, our fourth derivative is going to have me bringing this exponent p minus 3 down in front and multiplying it by all the other factors that are already out there. So we're going to have p times p minus 1 times p minus 2 times p minus 3 times our blob raised to a power decreased by 1. So it's times 1 plus x raised to this power decreased by 1, which p minus 3 minus 1 is p minus 4. Evaluating our fourth derivative at 0, you can see again that this is going to become 1. 1 to any power is 1, and therefore our fourth derivative evaluated at 0 is going to be p times p minus 1 times p minus 2 times p minus 3. I think it's obvious as to what's going on here, Stella. We can now develop in general ... the kth derivative, in general evaluated at 0. And look at the pattern here. The first derivative had 1 here evaluated at 0. The second derivative had p times p minus 1. Oh, you know what here? This should be p. I'm sorry. The first derivative value at 0 is 1 times, we forgot this p here. There should be a p here. So this should be just, this should be p. Yeah, your first derivative evaluated at 0 should be p. I apologize for that. Lost my p here. So when the first derivative value at 0 is p, and then the second derivative is going to be what? P minus 1. The third derivative, we have what? P minus 2. The fourth derivative, our last factor, is p minus 3. So do you agree our last factor always has, our last factor is always going to be p minus a number that's 1 less than the derivative? So the second derivative, we got p minus 2 minus 1 or 1. Third derivative, p minus 3 minus 1 or p minus 2. Fourth derivative, we have p minus 4 minus 1, which is 3. Okay, so in general, the kth derivative evaluated at 0, that being the case, technically up here, yeah, okay. So technically, our kth derivative evaluated at 0 is going to be p times p minus 1 times p minus 2 times p minus 3 times ... times our last factor is going to be p minus, okay, a number that's going to be 1 less than the derivative. So what's 1 less than k? That's going to be k what? Minus k minus 1. You recognize this though, Stella? If we clean this up and simplify this, what we really got here is we got p times p minus 1 times p minus 2 times p minus 3 times ... times p. Now we distribute our negative sign in here. So we'll have p minus k, and minus a minus 1 is plus 1. Doesn't this look hauntingly familiar? In fact, we've seen this, we've seen this before. We've seen this before. Where did we see it? We seen that way back at the top here. Isn't that the numerator here of this combination? Well, look at that. We have the numerator of our combination there. P in combination with K. We have the numerator of our combination there. Isn't that neat? So this would be the formula for the kth derivative evaluated at 0. This is the formula for the kth derivative evaluated at 0. It happens to be the numerator of that combination that opened up this document. Pretty cool, huh? How that works. All right. Okay, so that would be that there. Now let's look at the next problem here. Now it says, using the previous problem, find the Maclaurin series for 1 plus x to the p power. Well, that should be pretty darn simple. Maclaurin series of 1 plus x to the p power. You agree, we already have all the derivatives. evaluated at 0, centered at 0. So we should easily be able to write the Maclaurin series of 1 plus x to the p power. So 1 plus x to the p power, we should be able to write the Maclaurin series for this. Our first term of which is going to be just what, f of 0 divided by what, 0 factorial plus f of 1. I'm sorry, the first derivative evaluated at 0, excuse me, divided by 1 factorial, and this is going to be x minus 0 to the first, plus the second derivative evaluated at 0, which is over 2 factorial of x minus 0 to the second, plus the third derivative evaluated at 0 over 3 factorial times x minus 0 to the what? The third power, correct? Et cetera, et cetera. But we found all these derivatives. By the way, I don't think I found f of 0, but f of 0, let's see, let's go back here. I don't think I found f of 0 to start this out, all this here. So, but what would f of 0 be? Well, f of 0 would have me put 0 in here. So I would have 1 to the p power, which is just what, 1, correct? 1. F of 0 is 1. All right. So therefore, we can start to build our Maclaurin series here for 1 plus x to the p power. It's just going to be, this is, remember, 1 over 0 factorial is 1. So 1 over 1 is 1. F prime of 0, what was f prime of 0? Wasn't that p from the previous page? So this is going to be plus p over 1 factorial, which is just what, 1. Remember, this was just p. And this is just x minus 0 to the first power, just x. Plus, what was f? What was our second derivative evaluated at 0? Wasn't it p times p? What was it again? Our second derivative evaluated at 0. Right here was just p times p minus 1. So therefore, this is going to be p times p minus 1 over 2 factorial times x squared. Plus the third derivative evaluated at 0 was p times p minus 1 times what? P minus 2 divided by 3 factorial times x minus 0 cubed is x cubed. And you could go on forever with this. Plus the fourth derivative evaluated at 0 was p times p minus 1 times p minus 2 times p minus 3. And that's divided by 4 factorial times x to the 4th power. Plus on and on this goes forever. Okay. So this is your first term. This is your what? Second term. This is your, so this is like, let's see, this is like maybe your 0th term. This is your first term. This is your second term, third term, and 4th term. I don't know. Can we see any relationship between the term and the actual value we got going on here? Let's see here. Well, it looks like we keep adding one more factor of p, don't we, in the numerator there. As far as the factorial is concerned, it would be, this is over 0 factorial, this is over 1 factorial, this is over 2 factorial, 3 factorial, 4 factorial, and the power of x is also in sync with the index of the term. This is x to the 0th power, x to the 1st power, x to the 2nd power, x to the 3rd power, x to the 4th power. All right. So this would be the expansion. So how do we you know, show this here? How do we show our factors of P here though? Well, let's see here. Because we keep adding a factor of P. All right, I'm going to leave this like this for now. Trying to think here. If you got, I see notation where you got, let's see, multiplication here. If we have like P sub I goes from 1 to 2. I believe this means P sub 1 times P sub 2. Okay. But these keep getting decreased by 1. So let's see. Well, this is P minus 0. This is P minus 1. This is P minus 2. So what we could do here is we could say that the series, power series expansion of 1 plus x to the P is, to generalize this, we could just say that maybe this is, well, actually, I think we're going to have to leave it like that. Let's just leave it like this, Stella. Let's just leave it like this. So I've shown you the power series for 1 plus x to the P power. Okay. All right. That's good for that problem there. All right. Disregard that. Now they want you to find the first 4 non-zero terms of y equals 1 plus x. Y equals the square root of 1 plus x, excuse me. The first four non-zero terms. All right, they want you to find the first 4 non-zero terms of this. But do you agree that we can rewrite this as 1 plus x really to the 1/2 power? But do you agree we just developed the power series expansion for 1 plus x to the P power in general? Here it is. So what's my P? My P here would have to be 1/2. Do you agree? So therefore, our P is 1/2, and therefore we replace all these P's with what? 1/2 here. So the expansion of this thing, just following along with above here, is going to be 1 plus P. What's my P? 1/2. So 1 plus 1/2 times x plus 1/2 times 1/2 minus 1. So that's going to be 1/2 times 1/2 minus 1 over 2 factorial. Wait a minute. Let me take a look here. Let me look at this again. Oh, they want the first 4 non-zero terms. I thought it said non-negative terms. Okay, non-zero. All right, so we got that. So 1/2 times 1/2 minus 1 divided by 2 factorial times x squared. Plus this would be 1/2 times 1/2 minus 1 times 1/2 minus 2 over 3 factorial times x cubed. Okay. 1, 2, 3, 1, 2, 3, 1, 2, 3, 4. We found the first 4 terms here. And so therefore we'd have 1 plus, now we can clean this up. We got 1/2 x. And 1/2 times negative, and 1/2 minus 1 is negative 1/2. Negative 1/2 times 1/2 is negative 1/4. But 2 factorial is 2. So we have negative 1/4 divided by 2 is going to be minus 1/8. That's going to be minus 1/8 when you simplify all this. This is going to be 1/2 minus 1 is negative 1/2 times 1/2 is negative 1/4. So this is all negative 1/4. 1/2 minus 2 is 1/2 minus 4/2, which is negative 3/2. So what's negative 1/4 times negative 3/2? That's going to be 3/8, all right? And 3/8 divided by 3 factorial. 3 factorial is 6. So 3/8 divided by 6 is going to be 3 over 24, 3 over 48, which reduces down to 1/16. X cubed. And there you go. These would be the first 4 non-zero term expansion of the square root of 1 plus x. That's your answer for that problem there. And by the way, this was problem 11.3-9. All right, let's see, it's 12:08. I'm running, I got only a couple more minutes here before I got to run, but let's see. Now it says, using your answer from the previous problem, estimate the square root of 1.1. So they want us to estimate the square root of 1.1. All right, the square root of 1.1. Well, we can use this because we have the expansion here. So we will do that on the next page. So page number 11. The square root of 1.1 is going to be approximately equal to, well, hold on a second. It's not approximately equal to in this. Okay. So the square root of 1.1 is going to be equal exactly to the square root of 1 plus 0.1. Do you buy that? So what's our x? Our x is really 0.1, isn't it? 0.1. So as far as this expansion is concerned, our x is 0.1. So we're going to put 0.1 in here, here, and here to approximate the square root of 1.1. So again, our x is 0.1. X is 0.1. So therefore, we put in 0.1 in here, here, and here, and we'll crank out an approximation. So therefore, the square root of 1.1 is approximately going to be equal to, just following along here, 1 plus 1/2 times what? 1.1? I'm sorry, x is 0.1. We replace x with 0.1, not 1.1, 0.1. Because remember, our x is just 0.1. All right, so therefore we have 1 plus 1/2 times 0.1 minus 1/8 times 0.1 squared plus 1/16 times 0.1 cubed. And this will be a pretty good approximation here. So we get on our calculator and we'll dial this up. Okay. Well, let's see what we get when we bring that all up. And what I'm getting is about 1.0488125, which when you take the square root of 1.1, you do get approximately 1.0488088848. So you can see that we're pretty darn close. This is pretty darn close to this. Do you agree? And so there we go. We have approximated the square root of 1.1 by using our power series expansion for the square root of x. All right, one last problem, Stella, because this problem here, these last three problems are a real humdinger, okay? I was looking at these and these are really involved, the last three problems. I honestly don't think you'll have these last three problems on your exam. But these other ones are all fair game up to this point. Let's just try this one last problem. And unfortunately, I'm going to have to go after this last problem as I am running out of time here. Okay, problem number 12, or page number 12, excuse me. They want you to, using the Maclaurin series for 1 plus x to the 2/3 power, estimate. They want you to estimate 1.02 to the 2/3 power. Okay. Let me double check something here. Okay, all right. I just wanted to double check something there. Okay. Okay, so let's try this here. So f of x is equal to 1 plus x to the 2/3 power. And they want you to estimate a 1.02 raised to the 2/3 power. Let's see if we can do that. So let's see if we can do that. Okay, so they want us to use the power series expansion of this function to estimate this. Now, what have we accomplished so far to help us with this problem? Well, let's see. In general, this is the power series expansion that we've developed for 1 plus x to the p power in general. It's going to be this in general, okay? And then in general, it's going to be this. Now, we can use this power series expansion and tailor it to our problem. Because look at our p is really going to be what? 2/3. Do you agree? I'm going to put 2/3. P is going to be 2/3 here. So the power series expansion of 1 plus x to the 2/3 power is going to be 1 plus, replace p with 2/3 here, replace p with 2/3 here, 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 here. Okay, we got to replace p with 2/3 throughout. So therefore, let's write the power series expansion for this. So 1 plus x to the 2/3 power, its power series expansion is going to be, following along with this, it's going to be 1 plus 2/3 times x plus 2/3 times 2/3 minus 1 over 2 factorial times x squared plus 2/3 times 2/3 minus 1 times 2/3 minus 2, all divided by 3 factorial times x cubed. And I think that's good enough to go out the 4 terms there, plus and on this goes. Let's try to clean this up. So we got 1 plus, this is 2/3 x, this is 2/3, 2/3 minus 1, 2/3 minus 1 is 2/3 minus 3/3, which is negative 1/3. Negative 1/3 multiplied by 2/3 is negative 2/9. And negative 2/9 divided by 2, because 2 factorial is 2, negative 2/9 divided by 2 is going to be negative 1/9. Do you agree? Negative 1/9. So all this madness becomes minus 1/9 times x squared. Oh, let's see. 2/3 times negative 1/3 and 2/3 minus 2 is 2/3 minus 6/3. 2/3 minus 6/3 is negative 4/3. So what is 2/3 times negative 1/3? That's negative 2/9. Negative 2/9 multiplied by negative 4/3 is going to give us 8/27. 8/27. And 8/27 divided by 3 factorial is 8/27 divided by 6. So this is going to be 8/27 divided by 6. All this is going to be 8/27 divided by 6, which is going to be 8/6 times 27. 2 divides into 3, 6 3 times, divides into 8 4 times. So we're going to have 4/81. There you go. So all of this evaluates to 4/81. At least that's what I'm getting here. All right. So therefore we have plus 4/81 times the third x cubed. There you go. So this is the power series expansion, the first 4 terms for 1 plus x to the 2/3. Now we're going to use this power series expansion to estimate 1.02 to the 2/3 power. So I have a question for you. What is my x going to be? Well, in order for 1 plus x, in order for to the 2/3 power to be equal to 1.02 to the 2/3 power, in order for this to the 2/3 power equal to this to the 2/3 power, 1 plus x has to be equal to 1.02. Which means x has to be equal to 0.02. Therefore, x has to be 0.02. So therefore, we're going to put 0.02 in for x here, here, and here. So to evaluate or approximate 1.02 to the 2/3 power, this is going to be approximately equal to 1 plus 2/3 times x, but x is replaced with 0.02. All right, so now we need to dial this up on our calculator. 1 plus 2/3 times 0.02 minus 1/9 times 0.02 squared plus 4/81. Should be 4/81. 4/81 times 0.02 to the 3rd power. So getting on the calculator and dialing that up. Calculator is about to die. Square plus 4 divided by 81 times 0.02 raised to the 3rd power raised to the 3rd power. Let's double check and make sure I entered it all in correctly. This is quite a calculation. Good. And then we got 2/3 times 0.02 plus 1. Okay. I am getting approximately 1.0132892884. Checking our answer. If I was to take this 1.02 and raise it to the 2/3 power, I would get on a calculator 1.02 raised to the 2/3 power. I would get 1.0132892979. you can see that this is a pretty darn close approximation to this. And there you go, Stella. That is it. I am done. I got to run. I'm out of time. The last three problems on here are very involved problems. Okay, they're very involved problems. I can maybe send you a couple of videos that I have found that will help you to maybe gain some sort of traction on these problems, okay? But they're very, very involved problems. There's no way, I would be shocked if your instructor put these problems on an exam. These problems are not, they're not even in the scope of the realm of this level of a course. But I will post some videos and show you how you can, answer these questions if you're interested. It's a couple of YouTube videos I dug up, which are really amazing. I had a chance to look at them. It's quite a lengthy process to show these last problems, but I'll post the videos anyways for what they're worth if you have time to watch them. Okay, sorry I have to go. You have a great day, and hopefully I'll see you soon.